just to introduce myself, I'm PJ Freerick. I'm Managing Director of Air Composites, a company based here in the west of Ireland, just out the road. I will give you a presentation which describes two new technologies that we have developed for manufacturing large composite parts. In particular, our activity was based around wind turbine blades. And excuse me. And I'll explain the advantages of these technologies in manufacturing large composite parts, and also various other types of large composite or wind turbine blades and other types of composite products. The company Air Composites was founded by myself and Croher, who was introduced just a minute ago. He's also a lecturer here in the university, in 1997, and it currently employs 55 people, including 20 engineers. We are a supplier to a number of different aerospace programs, which includes the A400M, the A340, the V2500, which is an engine program, and also, as of this week, we are suppliers to the Bombardier Global Executive Jet program. We have a number of different processes which we use to manufacture parts. These include standard pre-preg processing in autoclaves and clean rooms, and which is used extensively in the aerospace industry. We also use RTM, which is resin transfer molding, and thermoplastic composite press forming. Our design department uses CATIA V5 and Patran Nastran, and we also have an accredited composite testing lab, CTL, and a joint venture with a Malaysian company, which is CTL Asia. Apart from our aerospace activities, we also supply products into the wind industry. We produce a range of small wind turbine blades up to 5 meters in length for up to 20 kilowatt machines. These again are produced in an innovative way, in that we produce them in one piece, so there's no joining or gluing together of the parts. It's produced one shot in a single piece. The single piece blade results in a much sharper trailing edge, and therefore your wind turbine is much quieter during operation. And the blades themselves have high durability. They're also lighter in weight, lower cost, and have a longer life. And the added advantage of being fully recyclable at the end of life. The process we use is environmentally friendly as well, in that there are no VOCs produced during the process, no smells, and so the environment in which the operators work is very clean. During the following presentation, which I will give to you about the new technologies, has three sections. The first one is section details the electrical heating tooling technology which we have developed. This technology started out in what we call the MEX system, which is mold efficient cooling and heating. And basically it was a system that was developed that would very efficiently heat molds and cool them without using ovens or any other equipment. The molds themselves that we worked with were metal, mild and stainless steel, cast aluminium or machined aluminium, or electroformed nickel. And the system worked by applying heating panels on the back or the B side of the mold, and then an insulating cover was placed over it, which was used in the cooling cycle when there was air intake and extraction points, which allowed the mold to be heated or cooled fast. This technology is currently being used to manufacture a number of composite parts, and the catamaran hull, which you see, which is illustrated, is a 15-foot hull, which is produced using an aluminium mould in 2 parts, with a mech tooling system on the B side of both those parts. The cycle time is typically 1 hour heating, 1 hour at temperature, and 1 hour cooling. The materials we use to manufacture is material glass fiber reinforced polypropylene, and it's a very high impact material which is ideal for that type of product. The problem, I suppose, not really a problem, but an issue that was apparent with the mech system was that because you had to use metal molds, there was a limit to the size you could go without having problems with the high cost of making the metal, and also the problem with the CT, or the high temperature thermal expansion of the metal. When a part, excuse me, somebody telling me something here, I should have knocked it off. The problem with the high thermal expansion of the metal caused stresses to be built up in the parts, and when you remove it from the mould, they tend to warp, and obviously the manufacturing of products that require accurate dimensions becomes a problem. The alternative material we looked at was epoxies and BMIs. However, materials that we were, like the material that we use for making the hulls, required to be processed at 200 degrees or so. The materials such as epoxies and BMIs, which are currently used to make tooling for the composite industry, however, would only really be useful up to about 180 degrees. Some materials, they will survive for a short period of time at higher temperatures, but they quickly begin to degrade, and the number of parts that you will remove from a mould after heating to that temperature usually is very low, and the life cycle of the mould is quite short. So we concentrated on materials based on ceramics, and these are ceramic cements. Our alumina silicates have very high temperature capabilities. They, however, are fairly difficult to reinforce with any fibre, glass or carbon, but they have got a very low thermal expansion, which was ideal for what we wanted. And so the technology that we produced, having worked with these, was this, what we now refer to as the thermoplastic composite reinforced ceramics, or TPC ceramic tooling. Ceramic reinforced, the technology consists of 3 elements: ceramic matrix, which is reinforced with the carbon fibre and PEEK fabric. The combination of these 3 materials gives you a significantly increased mechanical properties in the tooling, which is perfect for producing composite products. We also, instead of applying heating on the back of or on the B side of the mould, we embedded the heating system while manufacturing the mould. And this resulted in a very efficient heating system, which had the capabilities of up to 280 degrees without any degradation of the mould during cycling up to several thousand cycles. And because the ceramic is also a good insulator, it had the advantage of retaining the heat, and you had very little heat loss during the process, which made it a very efficient system as well. This illustrates how a mould is constructed. Once you have a pattern which can be made from standard tooling materials, our standard pattern materials machined for whether it's GRP or foam, that has been machined. You lay up the mould in a similar way that you would manufacture other moulds from other materials, where you have alternative layers of ceramics and carbon fibre peak. At the B side of the mould, we then lay in the electrical heating elements, and we seal the surface, or the A side of the mould, with a high temperature sealing system that gives you a vacuum tight surface. The excuse me. The use of this tooling in the composites industry opens up quite an additional number of possibilities for manufacturing parts. It also allows you to process resins which are currently used in the metal coating industry, but up to now you cannot process because no tooling was available that would go to the temperature required to process them. The advantage of these materials is that they are heat activated rather than chemically activated materials, and therefore you do not have the same problem that you would have with standard materials where you have thick sections and you have an exotherm which you have to control. So it allows you to speed up the process. Also, the nice thing about it is that you have the possibility of making complex parts in one piece without having to glue or join. In the case of the turbine blades, we were able to manufacture the entire blade as one moulding rather than as several pieces, which is the normal in the industry right now. Apart from wind turbine blades, this is a list of the type of areas that this technology or this moulding technology can be used in. And this is not a comprehensive list, but it certainly gives an indication of what the possibilities are. Wind blades, tidal and wave turbines, in the aircraft industry, boats, transport, trucks, etc. In the construction industry, you have the possibility for bridges, and also in storage, in the area of storage, you have tanks, etc., which is composites are currently widely used. In the next section of the presentation, I give you outline some details on the materials themselves, which I referred to earlier, which are what we refer to as powdered epoxies. There's a range of materials available, of thermoset materials available in powder form. They are materials that are used extensively to coat metals in the powder coating system. They have to be sprayed onto the metal and then heated to 200 degrees, and they are used for quite a few years now for this application. However, they've never been used as a matrix material in the composites industry. We would say we're first to achieve this. They have a lot of advantages over standard liquid epoxies and polyesters in that they are solid at room temperature, so they are easy to handle. They don't require any special storage in your factory, and therefore they're also more environmentally friendly to process. When you heat them to their processing temperature, they go to a very low viscosity, which means you can wet out the fibres perfectly. The heat-initiated reaction rather than chemical means that you can process them faster, even if you're processing very thick sections. Once you get above the temperature, the processing temperature of 180 degrees, you can achieve the very low viscosity, and also you eliminate the exotherm. You can also optimize the properties to suit the product, and you can have different properties in different layers of material in a single laminate. And of course, You get no VOCs or volatile organic compounds emitted during the process, and no styrenes, so you get no smells, etc., which is common to the industry. Despite all those, and usually in a situation where you get something that has a lot of advantages, there's usually some disadvantages. The one thing about these materials is that you do not compromise the resultant product, because the properties that you can achieve with them are equal, if not better in some cases, to most of the processes that are out there at the moment. The chart you see demonstrates this, where you compare three processes: an infused process, which is standard for manufacturing wind turbine blades currently; pre-preg, which is the upper end or the most costly process available for manufacturing them; and our powder process. And you can see that your properties are as good as the pre-preg or more expensive process, but the cost is in the lower end of the infused, if equal to, if not less than, the infused process. The final section of my presentation shows or demonstrates the manufacturing of a one-shot turbine blade, and shows how these two technologies are combined to give you a very efficient and cost-effective process. There are lots of advantages in putting those two processes together, in that you can, as I said, mould a blade in one piece, which results in being able to remove the blade from the mould without any additional post-moulding operations. Certainly they're very minimal in that there's no gluing or filling or finishing of the blade. The quality of the blade is higher because you don't have any glue or additional materials apart from your composite material, and because you've got you don't have any large glue lines on the leading and trailing edges, it makes for a much better blade. The fibres are continuous through the body of the blade, and so you don't have these areas which are always the areas that cause the most problems and requires the most quality control in order to ensure a good product. Also, the spar caps and webs of the blade are integrally moulded, and results in a much better and stronger blade. So how do you do all this great stuff? First of all, the first step in it is to prepare the material. The epoxy powder in this case is deposited on one side of the fibre mat. That is then cut to size and placed in the mould. The first step from there is your preform stage, which once you have it laid into the mould, you apply, you cover it with a vacuum bag, you apply a vacuum, heat it to 100 degrees. At that temperature, you can fully debulk the laminate, you remove all the air, and also you lock in the fibres in position, and they won't move from where they are after that. However, no polymerization has taken place as yet, so that when it goes through the next stage, it melts again, and the materials will flow to fill any joints or gaps that are there in the final assembly. So the three photographs show a spar, the bottom skin of a section of a blade, and the top skin being preformed. The next, which is the final assembly of these parts into the mould, starts with surface coating. Again, this is optional, but if you do this, it means that the product doesn't have to be painted or sprayed afterwards. All of these materials are powder-based, and therefore you get no issues with smells or VOCs. Once you assemble the parts into the mould, as you can see in the photograph, the spar being placed on top of the bottom skin, and then the top skin being placed over that. What you get is what you see on the left there. is that basically the mold or the blade has been reassembled, and all the parts, the component parts of it, are fit together like a jigsaw. There are no gaps or any joints in the mold or in the product at that stage. The final step is to place a vacuum bag inside, heat it up to 200 degrees and cool it down. And what you get is this, a part which has a surface finish on it. It's been molded all as one piece. That's the way it comes out of the mold. So you have no gluing, finishing or painting. The only post-molding work is to remove any flash that might be on the edge of where the molds join. We're now using this to build a 13-meter blade, and this is just some photographs of the steps we took to build the tool for that. An existing blade was used to form the master model, and then the ceramic materials that I described earlier was laid onto that to produce the part, or to produce the mold. And this is a photograph of the mold. It's totally self-contained. There's no other ovens, etc. required. All that's required once you have that is to put the raw materials in, preform them, assemble the part inside, put your vacuum bags inside, close the mold and plug it in. So what that does for the process is quite interesting, in that if you see on the left-hand side here, where a standard system is used to produce a skin of a blade, that you have, it may not be as visible in the photograph as I'd like, but what you see is lots and lots of tubes and bags and extraction points along the length of the blade. And this is used to inject in the resin into the fibre bed and extract any air out of it to allow it to wet out completely. Once that is complete, the entire bag and the tubing, etc., is then cannot be used again, because it's full of resin which is hardened at that point in time, and therefore there's a lot of waste in the overall production of a blade. Several 100 kilos of material are lost in the actual tubing, etc., that's used. The next stage in a standard process of making a blade is to assemble it. And the assembly process is the assembly steps require that you, once you have first of all manufactured all the component parts, the skins, spars, spar caps, webs, they're all assembled and glued together. Then the entire assembled blade has to be heated again to cure off the glue. Even when that's finished, you then have to go and tidy up all the excess glue, or if there's any areas along the trailing and leading edge that are seen not to have been perfectly glued together, you have to go and repair that and fix it. So the final step then is to do all that and finally assemble the blade. Our process eliminates all those three steps, because the blade, when it comes out of the mold, is as one piece and finished, except for some tidying up to be done. Okay, that was perfect. The conclusions from this presentation is that we have developed a system for vacuum processing of large thermoplastic composites. This new tooling system that we have developed allows the processing of heat-activated powders, which is highly innovative in that it hasn't been used in this way before. These materials, as I said, are can be either epoxy or polyesters, and we have demonstrated the use of these materials on a 13-meter blade. We currently have a limit of about 300 degrees centigrade at the moment, and we're developing the tooling further to get it to at least 400 degrees for the processing of materials such as PEEK, etc., which requires higher temperatures to do this. And this system also offers potential to manufacture large composite products with a higher quality than existing processes, and also at a lower cost. Thank you very much for your time. Any questions?